Hey learners, Jared here, and previously we were looking at Ohm's law and how voltage and current and resistance all were connected and affected each other. What we're going to dive into now is resistance and how is resistance determined for a particular material or object. To calculate resistance, we need to look at an object's resistivity. That is, its inherent ability to impede current or slow current down. Different materials have different resistivities, kind of like coefficients of friction. Smoother surfaces have a lower coefficient, so there are certain materials that will conduct electricity better than others. A better conductor is going to have a lower resistivity. It's kind of like a smoother surface with a lower coefficient. Now, when looking at a particular section of material, the other factors that we need to keep in mind, besides resistivity, how long is that material? How far does that current have to go through that particular material? And then what's the cross-sectional area for that current to actually travel through? All of these three things interplay with each other to calculate the overall resistance for a section of material. Looking at resistance and having it equal to an object's resistivity times the quotient between length and area. Seeing that will help you understand how resistance is affected by these other variables. You can see that resistance and resistivity are directly related. In other words, if you increase an object's resistivity, you are going to increase the resistance. Length is also directly proportional to resistance. The further that current has to go in that resistive material, the more resistance their overall is going to be. The area, though, is actually inversely related to resistance. In other words, the wider the cross-sectional area, the easier it is for that current to travel through. You can imagine it like a narrow door versus a wider door. A narrow door, a small cross-sectional area, means all of that current has to jam-pack in there, and it can't go as fast through that small cross-sectional area. But you open up the other door, you make a wider cross-sectional area, and overall the traffic can move faster. Now, length and cross-sectional area aren't going to have any other factors that can affect them, other than if you have the object heat up to the point where it actually contracts to where its length changes by a noticeable amount. But on that note, temperature can actually affect an object's resistance. Specifically, it will affect the object's resistivity. Increasing the temperature of an object is actually going to increase the resistivity of that particular material. You can imagine it like increasing the temperature is going to cause those particles to move around much more chaotically inside that material. And it's harder for the electrons to get through that material because there's all this traffic sideways, up and down, all around. It can't get through it as neatly. When the material is colder, its molecules are a lot more static, and it's easier for the electrons to navigate through that material, which is why lowering the temperature actually decreases the resistivity of a material. You can see how changing the length of that material is going to affect the overall resistance. The less material it has to go through, the less overall resistance there's going to be. Hopefully that gets you started and helps you kind of distinguish between resistivity and resistance and understand that resistivity is what determines that resistance. We'll dive more into circuitry and capacitors next time, and as always, keep learning.